Today we are working on 4.1, which is simplifying square roots. So if I had the square root of 52, can you tell me about what that number equals? It's between 7 and 8. So 7 squared is 49. That's a 4. And 8 squared is 64. So if you had to guess, what would you say? 7 point, do you think it would be 7.7? No. Why is 7.7 a bad guess? 52 is a lot closer to 49 than it is to 64. So it probably wouldn't be 7.7. 7.2, 7.3. I don't know, let's check. If I did the square root of 52, I get 7.2. So we're much closer to 7 than we are to 8, so 7.2. That was a good guess on my part. It's almost like I've done this before. Okay. Well, sometimes having the decimal makes more sense. In the practical world, that makes a lot more sense. You never measure a board and you say, oh, square root of 52. Nobody says that, right? You're going to say 7.2. But a lot of times in the mathematical world, having what we call the exact answer makes more sense. Because if you look at this decimal, 7.211102551, is that the end? No, it goes on forever. How do we know it goes on forever? We have a word for it. What type of number is this? Starts with an I. Not continuous. It's not a whole number. It's not an integer. It's not a natural number. Irrational. Irrational numbers go forever and never end. Okay? And the first guy who figured out that irrational numbers existed, it freaked him out. Because back in ancient Greece, the Greeks were under the assumption that every number could be written as a fraction. And then one guy figured out that there are numbers that can't be written as a fraction. And it scared him because everything they had done was based on the fact that all numbers were fractions. And they were drawing triangles and doing geometry, and the Greeks did a lot with geometry. And then one guy drew a picture and proved that this particular number cannot be written as a fraction. And he told all of his math friends, and there are two stories. We're not sure if either are true, but one is he rowed out on a lake with his friends in a boat and told them, showed them the proof and said, this number cannot be written as a fraction. And they beat him up and they threw him overboard. The other story is he took him into a room and told them that same news, and they beat him up and promised nobody let this out because it messes up all the math that we've been doing so far. But we don't know which story is really true or if either of them are true. But the fact is, the Greeks stopped doing geometry at that point. They quit doing geometry because they no longer trusted their shapes. And they moved on to algebra. And it turns out there are way more irrational numbers than there are rational numbers. Rational numbers are fractions. And there are infinitely more irrational numbers than there are rational numbers, which is kind of weird. What's that? Well, there's an infinite of all of them, right? There are an infinite natural numbers. There are an infinite integers, and there are an infinite number of rational numbers, and there are an infinite number of irrational. But there's actually a pretty easy way to prove that there are way more irrational numbers than there are rational. You really want me to blow your mind? There are just as many natural numbers as there are fractions, which is weird. You think there's a lot more, but it turns out there isn't. But as far as irrational numbers go, there are way, way, way more of those. And I could show it to you. I don't know if you guys would really like it. But one time when I was in college, I had class Monday, Wednesday, Friday, and my professor was going to be out of town for a week. And so we had another professor come in and teach our class. And instead of continuing with the math we were doing, which was really super advanced stuff that I'm not very good at, he decided to prove that the number pi is irrational. So he started the first day and he started writing this proof and explaining it and writing it. He spent a whole hour. I didn't understand anything he said. I just didn't get it. It was way over my head. And then the next day, Wednesday, he came in and did exactly the same thing. It kept going and going, and I was totally lost. And then on Friday, he came, and for the first half of class, he kept writing and writing and writing, and I was so lost at that point. And halfway through class, he said, therefore, that proves that pi is a transcendental number, and all transcendental numbers are irrational. And he said, we're done. You guys can go. Total waste of 3 days of my life. I'll never get that back. Well, at the time, I had no idea what a transcendental number is. I've since looked it up, and I understood what it is, but I couldn't even tell you right now what it is. I've forgotten. And he didn't prove that transcendental numbers were irrational. He just assumed that we knew that. So anyway, not something that I'm going to share in this class. But 7.21 whatever, it goes on forever. So no matter how we write this down in a decimal form, we'll never be totally correct. Even if we wrote 1,000,000 decimal places, we're not going to be totally correct. And because of that, all decimal versions of irrational numbers are called approximate answers. So what does the square root of 52 equal exactly? Well, as a decimal, you'll never know. There's no way to write them all down because it goes forever. Okay, so what we can do is simplify this down a little bit, and we create what we call the exact answer. And it's an answer that doesn't have decimals. It remains in square root form. And sometimes the square root form makes a lot more sense mathematically than the decimal version. It's a lot easier to work with in some cases. So the decimal part is super easy. You just plug it in your calculator. The exact answer is a little bit more complicated, but it's not difficult. So for 52, we factor it, and the answer is 4 and 13. Now, I could do 2 and 26. It doesn't matter. And then you continue to factor everything that has factors other than 1 in itself. So 4 factors into 2 and 2, and 13 does not have any factors other than 1 in itself. And you have to remember to ignore everything that factored. So the 52 no longer counts because it factored. And the 4 no longer counts because it factored. And now, because this is a square root, wait a minute, what does square root mean? What number times itself? Or we could say, what number squared equals 52? Have you ever figured out why squared is a 2 instead of a 4? It's the perfect two-dimensional shape, right? The height and the width are the same. If the width is x and the height is x, then the area is x squared. That's why it's a 2. So really, there's like a little imaginary 2 hanging out inside there, but because we're super lazy, we never write it. If it's anything other than a 2, then we stick it in that little crease. So we need to go through this list and grab every pair that we see. So I'm going to grab a pair of 2s. Okay. What do I do with that pair of 2s? Well, if we had multiple, we would times them together. But I grab that pair of 2s and I write a 2 on the outside. And I end up with 2 times the square root of everything that's left, which is 13. Okay. Now, that's what we do. And the video I had you watch, I don't think it explained why it worked. It just said this is how you do it. And this is a new class that I haven't taught, so I didn't have my own video. But the reason that works is because I am going to divide the pairs from the not pairs. And basically, I have 2 square roots. I have the square root of everything that had a pair times the square root of everything that did not have a pair. Well, the stuff in the pair would be 2 times 2, which is 4. And the stuff that did not have a pair is just 13. Well, what is the square root of 4? 2. And the square root of 13 doesn't simplify. So this is the simplified square root, and that is what we call the exact answer. 2 times the square root of 13 is perfectly correct. There's no decimal. It's not almost right. It's perfectly right. And a lot of times having that exact answer is more useful than having the decimal. Okay. What about this? The square root of 72. What does 72 factor into? 8 and 9. 8 is just 2 times 2 times 2, and 9 is 3 times 3. So, do I have any pairs? Pair of 2s and a pair of 3s. So, basically, the stuff that does factor, or does come out, what is 2 times 2 times 3 times 3? 2 times 2 is 4. 4 times 3 is 12. 12 times 3 is 36. And what did not have a match? 2. Now, what's the square root of 36? 6 times 2. Now, do we need to write this? No. We just say 2 times 3 is 6 and write it on the outside. But the reason it works is we are looking inside of the 72 and we're pulling out any number that's a perfect square. So the perfect square numbers are 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 16, 25, 36, 49, 64, and so on. So inside that 72, there is a 36 hiding in there. And the square root of 36 is 6. But there's also a 2 in there that stays and it doesn't come out. So if I had the square root of 150, so 5 and 30, 6 and 5, 2 and 3. And then I get rid of everything that factors. And this is called the prime factorization, meaning I keep factoring until every number in my list is prime. Are there any pairs? There's a pair of 5s. What do I do with that? I pull out a 5. And really what I'm doing is taking the square root of 5 times 5, which is 5. And then everything that does not come out stays inside the square root, which would be 6. 5 root 6. Does that make sense? Okay. What if I had the square root of 30? So that would be 2 times 3 times 5. What do I circle? Nothing. Does 30 have any perfect squares inside of it? Well, let's look. 4. Does 4 go into 30? No. The next one would be 9. Does 9 go into 30? No. The next one is 16. Does 16 go into 30? No. Does 25 go into 30? And then the next one's 36, which is bigger than 30, so I don't even need to try it. So the square root of 30 does not simplify because there are no pairs. And because there are no pairs, there are no perfect squares. There's nothing to simplify. So the answer is the square root of 30. That is the simplified version. It doesn't go any further. All right, now, what if I had this? How does that change things? I need 3 numbers to pull something out. It's not what times itself, it's what times itself times itself. So 81 is made up of 9 times 9, and each of those is 3 times 3, and I'm looking for triplets. Well, I have a triplet here and a leftover 3. And for every triplet, I write one of them on the outside. So 3 times the third root of 3. And what is 3 times 3 times 3? 27. And what is the third root of 27? 3. So we kind of skip that middle step, circle the triplet, and then write it on the outside. Does that make sense? Yeah? Hang on a second. Let me look at your assignment. All right, 4.1. Oh boy. So 4.1, we're going to be dancing all over the place because we're not going to do any of the fractions. So 5, 7, 8, and then and then 13 through 20 all. Now look at number 19. 19 hasn't, well, actually 20. 20 has an n to the 5th. How do you deal with the square root of n to the 5th? So you write 5 n's. N, 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 n. And then you circle pairs. How many pairs are there in 5 n's? 2 pairs. So for each pair, you bring one out. So what will be on the outside? N times n, because there are 2 pairs. And then were there any n's left over for the inside? Yes, so there would be an n on the inside. So, yeah, let me show you. So let's say I have the square root of 20x to the 3rd. Well, let's not do that. Let's do 20x to the 7th. So that's 2 times 2 times 5. Now, I've had a lot of experience. I can just do that in my head. And then x, 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 x. So 2 on the outside, and 1, 2, 3 pairs of x's. X to the 3rd, and then a 5 is left over, and an x is left over. So each one of those creates one of these x's out front. And then this and this just remain under the square root. So this is the answer. 2x to the 3rd times the square root of 5x. Yep. Okay.